Hello and welcome to this tutorial. Today we're going to be looking at graphing motion. So we'll be looking at producing displacement time graphs or position time graphs, however you want to call it, velocity time graphs, acceleration time graphs, and what to do to get that information. For instance, sometimes we'll have to find the slope of something. Sometimes we'll have to find the area under a certain part of a graph. Let's begin. Remember to pause or possibly rewind the video as needed. Let's begin. It tells us a car travels a constant means the same, right? 20 meters per second for 10 seconds. Fill out the table showing the car's displacement at the end of each second. Well, what does 20 meters per second mean? It means the car goes 20 meters every 1 second. So after 1 second, the car has gone 20 meters. After 2 seconds, 40. After 3 seconds, 60. After 4 seconds, 80. After 5 seconds, 100. After 6 seconds, 120. After 7 seconds, 140. After 8 seconds, 160. After 9 seconds, 180. And after 10 seconds, 200. So we're making ourselves a displacement versus time graph. We have displacement in meters on the y-axis. We have time in seconds on the x. So now we need to take a time to scale these axes. This is a good opportunity for you to practice. So at this time, pause the video, scale your t-axis down here and your displacement axis up here. Then you can plot the data points. All right, let's see how you did. I have to get to 10 seconds. Well, what I don't want to do is go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because then all my data is going to be grouped to the left side of the graph. So instead, I think what I'll do is I'll skip 2 boxes for every 1 second. So there's 1, 2, 3, 4, this would be 5 seconds. 6, 7, 8, 9, this would be 10 seconds. Okay. Then for the top one, I'm going to go every couple boxes is 20. So 20, 20, 40, 60, 80, 100 meters, 120, 140, 160, 180, and 200 meters. Okay, now at this point, go ahead and plot your points. So 20 seconds in 1, 40 seconds in 2, 60 seconds in 3, 80 meters, sorry, not seconds, 80 meters in 4 seconds, 100 meters in 5, 120 in 6, 140 in 7, 160 in 8, 180 in 9 seconds, and 200 in 10 seconds. Go ahead and draw your best fit line through there. And question 2 says, what's the slope of this curve? Whenever it says curve, by the way, curve means graph, okay? So the slope of that is, as you can see, up 20 over 1. Up 20 meters for every 1 second. That's 20 meters per second. How does this compare with the velocity stated above? It's the same. So the slope of this displacement time graph is the same as the velocity. Now for part 4, we're going to graph the velocity as a function of time. Well, it was going 20 meters per second, so after 1 second, it's going, well, 20 meters per second. After 2 seconds, it's still going 20 meters per second. After 3 seconds, still going 20, all the way across. In other words, constant velocity. Now I can use the same time scale, 1, 2, 3, 4, this will be 5, 6, 7, 8, 9, this will be 10. Okay, now for this one, I can go something to the effect of maybe 10, 20, 30, 40, 50, something like that. Which means I'd go at 1 second, I'm going 20, 2 seconds, I'm going 20, 20, and it's a horizontal line all the way across. looking like this. Well, the question says in part 5, what is the area under the curve for the first 5 seconds? So if I block this off, it's asking me to find the area under that rectangular region right there, which is the first 5 seconds. Now notice that makes a rectangular shape. So the area of a rectangle, if you remember, is length times width or base times height. Well, the base of this is 5. So if I want to go area would be 5 seconds times the height, which you can see is 20 meters per second. 20 meters per second. Notice the units of second cancels, leaving you with the unit of meters. So the area is 100. How does this compare with the displacement for the first 5 seconds? You can see it's exactly the same. So the area under a velocity versus time graph is the displacement. Okay, so if we summarize, now 3 of these are summarizations, one of them is a new introduction, but if we go to slope of a displacement time graph, you get the velocity. If you take the slope of a velocity time graph, well, that gives you acceleration. We're going to get into that one in a little bit. Now, the area under an acceleration time graph. Well, what does it mean to accelerate? It means to change your velocity. So the area under an acceleration time graph is your velocity. Now, specifically, it's your change in velocity, but we'll simplify it just to velocity. Now, the area under a velocity time graph, that gives you your change in position or your displacement. So we need to now answer the next 8 questions pertaining to this displacement versus time graph. Question says, how far does the object go in the first 5 seconds? Well, 5 seconds, you can see it goes 5 meters. During the next 5 seconds, well, you can see the horizontal line there, it didn't go anywhere. It stayed at 5 meters. So 0, didn't go anywhere. During the third 5 seconds, you see it goes from 5 to 15, so it moved 10 meters. During the next 5 second interval, it went 0. During the last 10 second interval, it went negative 15 because it went from 15 back to 0. This indicates the negative slope that you see here. During which interval is the object standing still? This means constant position. Constant location. Well, the only place you have constant positions would be here and here. So in other words, from 5 to 10 seconds and from 15 to 20. Does the car ever accelerate in this scenario? Yes. When we're going from a speed to at rest, you had to accelerate right there. Here you're going from at rest to a speed, which means you had to accelerate right there. Here you're going from a speed to at rest, you had to accelerate right there. And from at rest to a speed, you had to accelerate right there. So at 5, 10, 15, and 20 seconds. Now to create the velocity time graph for this, go ahead and make your axes. And to get the velocity time graph, we're going to get the slope of the displacement time graph here. Now there's how many line segments? 1, 2, 3, 4, 5. So we're going to find 5 different line segments, 5 different slopes. And we'll write the slopes on here. Up 5 over 5 this is a slope and a speed of 1 meters per second. Flat line No rise, 0 meters per second. The third line, you're going up 10 over 5. Well, up 10 over 5 would be a slope of 2 meters per second. Flat line again, 0. And for this bottom one, you're going down 15 over 10. That's going to be negative 1.5. So I'm going to plot those. Okay, first I need axes, so use the same time axis, 5, 6, 7, 8, 9, 10, 15, 20, 25, 30. And I can go something to the effect of 1, 2, 3, negative 1, negative 2, negative 3, something like that. Okay, I'm plotting my lines. My slopes as lines. So I'm going to go 1 meter per second for 5 seconds. That's that slope there. Then I'm going to go 0 for 5 seconds. So that would be plotting my velocity down here. Then my third interval is plotting 2 meters per second, again for 5 seconds. My fourth time interval, again, 0. And my last time interval is negative 1.5. That's why I needed the negative scale down here. So that would be here for those last 10 seconds. Notice I did not connect them vertically. Okay, you can leave them discontinuous, that's fine, that would still be correct. Now we're given a velocity versus time graph. This is a typo, by the way, this should be meters per second. We're given a velocity versus time graph. Well, it says, number 19, during which intervals is the object accelerating? Well, you're accelerating when you're changing your velocity. So I'm changing my velocity here, 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 and here. I have a constant velocity of 15 meters per second right there. So I'm accelerating A, B, D, and E. When was the acceleration the greatest? Steepest slope. When is the object standing still? None. Don't be confusing this one with this one. These are from a displacement time graph, which is constant position. Constant position of 5, constant position of 15. It means you didn't go anywhere. That means you didn't move anywhere. It means you don't have any speed. Here, this is a constant velocity of 15. So nowhere in here is it standing still. To show standing still on a velocity time graph, it would have to be a horizontal line at 0 velocity. And that didn't happen in this graph. When does the object have the same speed? That would be up here, part C. Now, part 23 through 27, we're finding displacements. Well, in order to do that, we have to find the area under these segments. So I'm going to find the area right here. So segment A is this triangular region right there. Notice it has a base of 5, a height of 5. 5 times 5 is 25. Half of that is 12.5 meters. This trapezoidal area, all of that, can be broken down into this triangle and that square. The square, 5 times 5, that's 25 meters. The triangle, 5 times 10 is 50. Half of that is 25 meters. Add these together. Okay, and so far we've got 12.5 meters and 50 meters. Last one, we have a base of 5. We have a height of 15. We're looking at 75 meters. Interval D, this trapezoidal region all right here. Break that down into a big 10 by 10 square. 10 times 10 is 100. And that triangle right here has a base of 10, a height of 5, that's 50. Take half of that because it's a triangle, that would be 25. Add those together, we're at 125 meters. This can also be broken down into a trapezoidal region, 12.5, just like the initial triangle here. And this square is the same as that one, so that would be 25. Add those together, we're at 37 and a half. Now, to find the acceleration time graph, you need to find the slope of the velocity time graph. Okay, so we're finding an acceleration time graph here. Acceleration versus time. So we'll have acceleration in meters per second squared is the unit for acceleration. That's brand new to us. Go ahead and make your axes. All the way across. We can go 1, 2, 3, -1, 0, of course. -1, -2, -3, and use the same time scale as we did before. So 5, 10, 15, 20, 25, and 30. Okay, so I just got to find the slopes of these parts here. 1, 2, 3, 4, 5 slopes. So let's find those slopes. I'm going to write them on here, and then we'll transfer those as my accelerations down below. Up 5 over 5, that's a slope of 1. Up 10 over 5, that's a slope of 2. Not meters per second, but meters per second squared. This is acceleration now. Slope of 0, that means 0 acceleration. Now part D, I'm going down 5 over 10. That would be -1/2 or -0.5. And here I'm going down 5 over 5, so that would be a slope of -1 or -1 per second squared. All right, plot them. So this would be my first acceleration right here. And then I'm going to go 2 meters per second, and then 0, right? I'm just plotting these numbers right here. And then after 0, it's -0.5 for 10 seconds, and then -1 for the last one. Okay. Now, for the very last page, you're going to be given either a position time graph, velocity time graph, or possibly an acceleration time graph. And we have to be able to come up with the other two. Okay? Now, the first set are pretty doable. When we start getting into curves, we need to establish two different possibilities. When our slope is flat, we start with a flat slope to a steep slope. You'll hear me say the phrase flat to steep. That means your slope is getting steeper. Or you could start with a steep slope and end with a flatter slope. That's steep to flat. Okay, we'll talk about that one shortly in terms of what those two things mean. All right, so what do we have in our first one? This is showing you a straight line. Remember if you have a position time graph, so let's kind of draw this up. If I have a position time graph or a distance time graph, and I find the slope of it, I get velocity. Now, if I find the slope of a velocity time graph, I get acceleration. So the slope of displacement gives me velocity. The slope of velocity gives me acceleration. This is a straight line, which is a constant slope, therefore constant velocity. Well, how do I sketch constant velocity? Notice, by the way, it's a positive slope, so it's constant positive velocity. Well, what kind of acceleration is this? This is acceleration equals 0, so I'm going to plot 0 acceleration for the same time interval here. This is also showing you a straight line in number 30, but now this is negative slope, so this is negative constant velocity. We can sketch that with a horizontal line under the t-axis like that, forever how long this goes, which is also 0 acceleration. 31 is a combination of 29 and 30, the first half and the second half. So this is positive constant velocity, this is negative constant velocity. So I would have something that looks like this. Both of these are 0 acceleration, so I should have horizontal line at 0 all the way across. Now when we get to 32, I'm going to come back to 32 in a minute because it's starting with a velocity time graph. So let's tackle these position time graphs here, and then 32 will make more sense. Okay. Now, above 33 through 36, let's write the following phrase. When your slope goes from flat to steep, your object is speeding up. Speeding up. When your slope goes from steep to flat, you're doing the opposite of speeding up. You're slowing down. Now, the thing about acceleration is it requires a couple things. Positive and negative direction. Positive direction would be right up forward. So if you're going to the right, upward or forward, that's a positive direction. If you're going to the left, down, or backward, that's a negative direction. But you're also considering speeding up and slowing down. Speeding up is a positive change in velocity. Slowing down is a negative change in velocity. If you put these two together, positive direction speeding up, that's positive constant acceleration. CA stands for constant acceleration, by the way. If I'm slowing down in a negative direction, that corresponds to negative constant acceleration. Slowing down in a positive direction, the two of those correspond to a negative constant acceleration. And slowing down in a negative direction, would be positive constant acceleration. And I don't know if you guys see the analogy here, but it kind of looks like what happens when we multiply integers. Positive times a positive is a positive. Negative times a negative is a positive. Negative times a positive is a negative. So it looks a lot, it's very analogous to what happens when we multiply integers too. So this is a good resource to tell us about the overall nature of acceleration. All right, here we go. Let's put this together. This is showing me flat to steep. This means the object is speeding up. That's number one. And these are positive slopes. So I'm going to say speeding up going forward, meaning in a positive direction. That's what? Positive constant acceleration. Whereas 34 is going steep to flat slope. Now the object is slowing down. Slowing down, going forward. I know it's going forward because it's still positive slopes. Well, this is negative, this is positive. These combine to give you negative constant acceleration. So how do I plot that on the velocity scale? Well, here I'm starting with zero slope, so zero speed to start with. So let's plot a line, dot at zero. Here I'm ending with a steep slope, so I'm ending with a higher velocity. So at this time frame here, I'll have some velocity that's a lot higher. Connect them with a straight line like this, the slope of which is positive what? Constant acceleration, just like we see there. How do we plot that here? Horizontal line across. This is positive, this is zero, that's negative, right? Okay, how do we plot this? Well, you're starting with a speed and you're ending with a flat slope, so you're ending at zero speed. So I'm starting with a speed to represent my steep slope, and I'm ending with zero velocity down here. Connect those two with a nice straight line. This is negative slope or negative constant acceleration, just like we saw right there. How do I plot negative constant acceleration? Horizontal line under the t-axis. Okay, now in this one, I'm starting from what? Steep to flat. So steep to flat means I'm slowing down. Well, slowing is a negative change in velocity. Notice it's a negative slope also. So that means I'm going backward or to the left or downward. That is also negative. These two together combine to give you positive constant acceleration. Okay, so how do I plot that? I start with a negative velocity down here. I end with zero velocity over here. Connect those with a straight line. Notice it's an upward slope, meaning positive constant acceleration, just like we saw there. And I can plot that as a horizontal line across like that. Remember, positive, zero, negative. Now, 36, if you notice, is the same as this and this combined. So if you put that together, you get what? At this point here, I'll make a mark to represent time t as the change. I'm going to have this just like that. And this part is going to look like that. Acceleration-wise, this is positive constant acceleration. This is negative constant acceleration. So it might look like this. Now, you should be able to see by now 36 is exactly the same as 32. You just started with this graph here. So I'm going to fix that by going concave up right here and then concave down. Oops, sorry. Concave down like that, which would be positive constant acceleration, negative constant acceleration. Okay, 37. I'm starting with 33. You can see that. But then I'm ending with flat to steep. So I'm starting with flat to steep. So what am I doing for the beginning here? So for this part, I'm speeding up, that's positive. Going forward, that's positive. This is positive constant acceleration here. But if you notice, I'm also going flat to steep, but in the negative direction. This is also speeding up, but it's doing so backwards. That's a negative slope. You're going backwards. That's negative constant acceleration right here. Okay, so how do I plot that? Well, go 0 to some time t. Okay, and there's my first graph right there. Positive constant acceleration. But then I have to start at 0 again, which is very strange. That wouldn't happen in real life. I'm starting at 0 again, going to some negative velocity value over here. Like that. And that right there would be negative constant acceleration. And I could plot that something like this. Okay, now finally in question 38, 39, and 40, you're simply putting together 3 segments. So I'm going to have, let's make a mark here, here to represent the change of the times. Here, here, and here, here. Okay, so what's this going to look like? Well, constant position, that means I'm what? I'm not moving. So that's 0 velocity. So 0 velocity, or you could say constant velocity of 0. This is negative constant velocity, and this is 0 velocity. So negative constant velocity, 0 velocity. All of these are showing you no change in velocity. So it's 0, 0, and 0 acceleration all the way across. Here, we're dealing with positive constant velocity, 0 meters per second, 0 velocity, and negative constant velocity. Would look like this. Positive constant, 0, negative constant velocity like that. Again, none of these is showing you a change in velocity, therefore it's 0 acceleration all the way across. And in our final one, this one is now a velocity time graph. So this is showing you positive constant acceleration. This is showing you constant velocity, positive. It's positive constant velocity because it's above the t-axis. If it were a line down here, that'd be negative constant velocity. and this is showing you negative constant acceleration. So what would that be? Well, I could do my acceleration graph first. That's easy. So positive constant acceleration. Constant velocity means zero acceleration. So zero acceleration. And negative constant acceleration looks like that right there. Okay, now this graph here would be speeding up going forward. That would be flat to steep, like that. This is a flat straight line going like that. So I've got positive constant acceleration, positive constant velocity, and then this part here is going from some velocity down to zero. That would be steep to flat, like that. Okay, I hope you found this tutorial to be helpful. Thank you. We'll see you next time.